So if you're at the APS, do people here attend the APS March meeting? I'm trying to remember, next year it's in Denver in March. The Rock and Roll Physics Sing-Along has a live band and many performers. I'm only one of many volunteers. And it happens Wednesday night of the conference. It's organized by a guy named Walter Smith from Haverford College. And he's always looking for volunteers if you play an instrument or you want to sing or otherwise perform something at the Rock and Roll Sing-Along. You're also welcome to write your own parody songs. Take your favorite secular, non-physics related tune. I don't know, what's the hot song on the radio right now? Take that song, add physics lyrics, and it will be a hit in Denver. Okay, so one thing I've been really impressed by in my, this is my first visit to UC Riverside, is how much cross-disciplinary physics is happening at this university. We have a lot of deep and rich knowledge in life sciences that is interplaying with physical sciences. And in general, I would say it's a trend in physics that physicists are embracing physics problems that fall outside of what we used to think of as physics, right? Because physicists can learn anything because physicists are awesome, right? So we are knowledge sponges, and once we step our foot into a field, we can bring tools and methods from other disciplines where we have worked into whatever field we step into. So for instance, using the Ising model to study the genome. Like, who would have thought, right? Really cool things. So today I'm going to tell you about my excursion into what might have been known as polymer physics, or polymer chemistry, mechanical engineering, and device engineering, which is a little far afield for a physicist. So I'm going to tell you about shape transforming materials that are programmable. In other words, you can structure a material that when you stimulate it, it will go from one shape to another shape. And not just like a shape memory material that has two shapes that it remembers, but that you can program the choreography of all the trajectory of motion from one state to another state. The class of materials I'm going to be telling you about is liquid crystal elastomers. Okay, so the first question I have to ask is how many people here know what liquid crystals are? Okay, so not everybody. So liquid crystals are mesophases, the same way that crystal, liquid, and gas are phases of matter. There are mesophases that are intermediate in their degree of order compared to those other standard phases that you've been studying since elementary school. Okay, and what makes these materials special is that the molecules are not spheres. They can be rod-like, and the picture I have for you here is showing mesophases of rod-like molecules. If you have a liquid crystal device in your pocket, and I know you do, right? You have liquid crystal displays on your cell phone, on your laptop. You might have them on your smartwatch, but a lot of smartwatches these days are OLEDs. So liquid crystals are not everywhere, but they're in a lot of places. If that material is really cold, it'll have a crystal structure. Okay, and here I'm not showing you any chemical detail. I'm just coarse graining. Let's imagine these molecules are kind of ellipsoidal and they're prolate. Okay, so their crystal structure will have some unit cell. Okay, and if they're really hot, they'll be isotropic, which means not only their centers of mass are random like any other liquid, but their orientations are also random. They might have short-range correlations, but in general, they're random. If you cool a material, if the aspect ratio is about 5:1 or larger, those materials on cooling will undergo a transition to a nematic phase. The word nematic comes from the Greek word for thread. You've heard of nematodes, right? Those are elongated biological creatures. They're not named for the shape of the molecule. They're named for the shape of the topological defects that form in them. The defects are disclination lines, and when you look through a polarizing light microscope, the experimenters saw a mass of threads, and they called it the thread phase, the nematic phase. Some materials have other mesophases. For instance, there can be smectic phases. If you leave your soap in the soap dish in the shower and a little water collects there, you get that mushy, squishy, dissolved soap. That is a smectic phase. The surfactants have formed bilayers, and the bilayers have stacked into a lamellar structure. That's a smectic phase. You see layers. Okay, but if you took one layer, like a chest of drawers, if you pulled one layer out and look from the top, you see disorder. Okay, and in the smectic A phase, the average orientation of the rod-shaped molecule is parallel to the layer normal. However, if you keep cooling, some materials have another smectic phase called a smectic C phase where they tilt. And once they're tilted, if you look at the tilt from above, it defines vector, kind of like in the XY model, for if there are any statistical physicists here. So that can have point defects. So, and the layers themselves can also have edge dislocations or screw dislocations, can occur in smectics. And there's actually a whole zoology of other mesophases that can arise. And what if your molecule is shaped like a disk, like a pizza or a coin, instead of a rod? Can also form mesophases. They can stack like columns. The columns can be ordered or disordered. We can also put, there's a food dye called sunset yellow, which I believe is a prime component in Doritos or Cheetos. It gives it that lovely golden hue. Sunset yellow in water, the molecules are shaped like checkers. The checkers aggregate into columns, and the columns align and form a nematic phase. That's a lyotropic liquid crystal. It changes phase with density, like how much sunset yellow you put in the water, okay? In this case, this is a change of phase with temperature. We call those thermotropic liquid crystals. Okay, the liquid crystal that's in your cell phone, in the display, do you know how that works? The molecule itself has a dipole moment. It can be reoriented by an applied electric field. And it's so sensitive that a tiny, tiny electric field is enough to make it want to rotate. In a conventional twisted pneumatic display, did you ever buy like an $8 alarm clock at Target? Or a big box, or a little cheap liquid crystal display, or the calculator at the dollar store? They're not sophisticated displays. Like the one you have in your pocket is a little more sophisticated, but the simple one. The liquid crystal is north-south on one surface because the material has been rubbed so that the liquid crystal lies, with their rod-shaped molecules, they lie parallel to the north-south direction. And on the other face, east-west, in between they twist. You put a little bit of chiral dopant in the liquid crystal to make it always twist in one direction, okay? And then you put cross polarizers. And because of the twist, light can actually get through the cross polarizers because the light rotates through the twist, okay? But then when you apply an electric field, boop, all the molecules go parallel to the electric field between the top and the bottom surface, and no light gets through. And that's the black part of the display, like those little segments that make the letters, or make the numbers on your $8 alarm clock from Target. Okay, there's been inflation. Maybe now it's $12.99, but it's a cheap liquid crystal display. Okay, so these liquid crystals change their optical response and their microstructure, like their phase behavior, with temperature. Did you ever have a mood ring? Mood rings were very popular in the 70s when I was in elementary school. Those are cholesteric liquid crystals. So the liquid crystal can either, the molecule itself can be chiral. Okay, so for instance, like take 2 pieces of uncooked rotini next time you are cooking rotini in your kitchen, put them side by side, push them together. They do not lie parallel well. Because of the screw shape, they will want to twist a little bit. It's actually a fun demonstration for children. You can boil your rotini just briefly to soften it up a little, and then take a needle and thread and go sideways through the rotini and put a whole bunch of them on a string. And you know what they'll do? They'll make a spiral. Okay, so in a cholesteric liquid crystal, if the molecules are chiral, you will get a twist. So that means the long axis of the molecule is locally parallel to its neighbors, but over a distance of, say, microns, it will rotate. Okay? And it might be that if you have a material that's not chiral, like these nice smooth round rods, they're not chiral at all. But you can add a little chiral dopant, a little chiral stuff, and it will induce the twist. So cholesteric liquid crystals, the distance over which they twist is very sensitive to temperature, and that's how mood rings work. The distance for a twist controls the wavelength of light that's reflected, and when it's warm, it's blue, and when it's cold, it changes. And actually, there are some chiral dopants where the distance decreases with temperature and some increase with temperature. So it's one of those great mysteries of life, how chirality occurs in condensed phase materials. It's really fun. So I hope you will all, I think mood rings are hot again. And I just heard there is a hair dye you can buy that will actually, you can put mood color in your hair, and your hair will change color with temperature. Like you go out in the sun or use your hair dryer, it'll change color. I just learned about that last week, or I would have put it on in time to come for this talk. But it's definitely on my list of things to do. So liquid crystal elastomers are not liquids. They are elastic solids, just like rubber. Okay? They are a kind of rubber. They're a polymer. And let's see, what can you see here? I think I have to go this way. Okay, so here's this coil, and inside the coil, I'm sorry, it's not easy to see. There's a very thin little piece of plastic there. And what's going on in this coil, when we run current through the coil, When I say we, I didn't do this experiment. When Ratna and Jawad Nassiri at the Naval Research Lab ran current through this coil, they heated up. And when the material gets hot, it shrinks. And I was really confused by that. When I was a little girl, my mother told me, you know, things expand when they heat up. And like this one shrinks when it gets hot. This one, I'm sorry, it's not a video. This is, looks like a diving board. It's attached on one side. And when you blast a laser pulse on the top, it flips up. This experiment was done by Peter Palfi-Mahore at Kent State. And here's a third one. This is also a group from the NRL group. This is a smectic elastomer. It has conforming electrodes front and back, which is just a kind of conducting grease. And when they apply a voltage, it twitches, it twists, right? So these are materials that mechanically respond when stimulated. They don't just change their color like a mood ring or turn a pixel on and off like in a conventional liquid crystal display. They flex like a muscle. And that's odd. I mean, that's really unusual. How many pieces of material do you have that act like muscles? It's an actuator. Okay, so how does it actually work? So let's see, this one is done by heating and cooling. This is a light stimulus, and this is an electric field stimulus. There are also some materials that will respond to the pH of their environment. Yes?
What's the length scale on the right?
I think that is centimeters, or maybe like 1.5 centimeters. I'll have to go back and look at the paper. I'm a co-author of that one, so you can find it on my Google Scholar page. Okay, so what is the mechanism? Okay, so the first one with temperature is just a pneumatic isotropic transition. So at cold temperature, the material is pneumatic. So here we have liquid crystal molecules. We call them mesogens because they produce mesophases. So just think of them as little rod-like objects, little rod-like molecules, and they can be, here I show them dangling off the polymer chain. They can also be incorporated in the chain, kind of like links of sausages. You can have the mesogens in the main chain. And actually when they're attached to the chain, they can be side on here, or they can actually be end on. There's various varieties. But the key issue is when you raise the temperature, they go through an isotropic pneumatic transition. So at cold temperature, they're pneumatic. That's the aligned phase. At high temperature, they're disordered. And they basically pull the polymer chains along for the ride, and they make the material shrink along the axis. In the case of light, the material is doped with a azo dye. The generic name is azobenzene, and this is a material that undergoes photoisomerization. So the molecule has two different states. The relaxed state, the low energy state, is rod-like, and when it absorbs a photon of a specific wavelength, it will undergo a transition to a bent shape. So trans is this one, and cis is that one. If you have any chemists in the room, they know probably 20 times more about this than I do, so please don't ask me the chemical details. But in that case, when you take a rod-like object, it fits very neatly into the pneumatic phase, but when it disorders, or when it undergoes a conformational change to a bent shape, it disorders the liquid crystal and also drives the material to shrink. What's interesting is most of these materials are not entirely transparent, so if you shine light on it, only the part that receives the light will shrink, and the back will not. Okay, it just depends how transparent the material is. Okay, and then in the third case, we have a smectic elastomer that has layers. And so here it's shown in the smectic A phase. That's the one where the molecules are aligned parallel to the layer normal. And then when you apply an electric field this way into the board, that induces a tilt. So, and when all the molecules tilt, think what happens when you have books on a shelf and they tilt. Their spacing this way gets smaller. So we expected that the electric field would just make the whole thing shrink, but instead it twisted. And it turned out that was because when the material was cross-linked, there was a little asymmetry. So the polymer is formed between two pieces of glass that align the liquid crystal, and when they take it away from, they put the liquid crystal, the monomer, and the cross-linking agent between the two pieces of glass, and then they shine UV light on it to polymerize it. And if the top gets a little higher cross-link density than the bottom, that asymmetry is what turns what should be a stretch into a bit of a twist. So it's the asymmetry that drives that one. Okay, now so far, all the things I showed you have a very simple pattern where the pneumatic director, the director of the liquid crystal is the average orientation of the long axis of the molecules. But we can pattern it. So here's a picture of a bullseye pattern. Okay, so imagine the pneumatic liquid crystals in the polymer are all lying parallel to those lines in a target shape. Okay, so we call this a +1 topological defect because if I take my pen and lay it parallel to the axis of the molecules, I'm not quite tall enough to do that, but going around, my pen would rotate by 1 rotation in the plus theta direction, which is the counterclockwise direction. Oh boy, you can really see how stretched this image is because those are supposed to be circles. Okay, so anyway, the +1 defect actually, when you actuate it, doesn't stay flat. It pops into the 3rd dimension and you get a cone. Okay, that means we have programmed, by putting this circular pattern into the pneumatic director, we have programmed a shape transformation from a disk to a cone. And it's not a perfect cone, it has some roundedness at the tip. We can also induce a twist, just like in your, the display in your cell phone, or any conventional twisted pneumatic display. We can put a twist in by rubbing the substrates so that on one side it wants to go north-south and on the other side east-west, and we can get a 90-degree twist. And again, we have to add, just like in the display, a little bit of chiral dopant. If you have a 90-degree twist and the material's not chiral, it could rotate clockwise or counterclockwise, and you could have domains of each which would be separated by defects. So to make sure there are no defects, put in a little bit of chiral dopant, you could always twist the same way. In this picture, I don't know if you can tell, this is twisting from +45 degrees to -45 degrees. So right at the center of the film, the pneumatic director would be parallel to the long axis of this ribbon. And we can also put a splay pattern in, where on the bottom, the pneumatic liquid crystal is parallel to the bottom of the material, the bottom of the substrate, and vertical on the top. And all of those things program different types of deformation. So for instance, you could get, in this case, you could get a bend. And in this case, you can get a twist. And if the material is narrow, if you have a ribbon that's narrow, you'll get something that looks kind of like a rotini noodle. Okay? And if it's wide, you get something that looks more like a paper towel roll that's been unwrapped. Okay? And actually, there are some beautiful elasticity calculations where we can tell you when you get one structure or the other. We spent a lot of time figuring that out, but to be honest, I'm not sure anybody really cares. But it was a fun problem. Just to let you know, this particular experiment was done at the Technical University of Eindhoven in the Netherlands. And in this case, this little cone is held onto a pipette, which has suction. So they were like holding it up and then shining a heat gun on it to make it transform. That way you didn't have to like hold it with your hands or hold it with the tweezers. This experiment was done at the Air Force Research Laboratory in Dayton, Ohio, and they floated their sample on water because it's really hard to like hold it. And so they're viewing it from above here, and so this cone looks kind of like a volcano, if you're like looking down at a volcano. Okay, so the question is, how do you actually get that pattern in there? So as I said, you can decorate the bounding surfaces. If you form the material between 2 pieces of glass, they can be patterned. So the simplest way liquid crystals were controlled, orientation was controlled at a surface in the early days of liquid crystal displays. And by the way, liquid crystal displays were invented at Kent State. It turns out it was actually, there was a fight over who owned that patent, and Kent State at least got a piece of it. But just rubbing, like you can rub the glass and you make little ridges and the liquid crystals try to align with those little ridges, right? So that's one way to do it, but there are other ways. The material can be cross-linked, the surface material can be cross-linked with polarized light that orients it. So we have different mechanisms for patterning the surface. So if we have 2 surfaces that have that target pattern inscribed for anchoring the liquid crystal at the surface, then we can put in the monomer, the liquid crystal, the cross-linking agent, shine the UV light through the glass, and then remove the material from the glass, and we get that pattern there. So that was the old way, the first way that these materials were patterned. The name for that is called blueprinting. Okay, so you basically impose a vector field in your material. It can be uniform through the thickness if you use the same pattern on the top and bottom surface, or they can have a twist or some other thing. And then there's another way, which is called 4D printing. Have you heard that term before? We all know what 3D printing is. That's, additive manufacturing, where it's like when you put toothpaste on your toothbrush, except you like build a fort out of it, right? That's 3D printing. Did you ever try that? Okay, I bought a very odd thing. It's called a cheese doodler. It's a real actual product. I heard about it on a radio show called Wait, Wait, Don't Tell Me. It's basically a glue gun, but instead of putting glue in it, you put cheese. In fact, you can buy a cheese stick, which looks more or less like the thing you put in your glue gun, right? You can stick it right in there, and you can use it. You can't actually build a fort out of cheese, because the cheese doesn't solidify hard enough, but you can build a fort out of like cheese and crackers. You should try it sometime. Anyway, so that's 3D printing. 4D printing is when your 3D printed object changes shape after you build it. And I was introduced to that concept by Sabeta Matsumoto, who was a postdoc at Harvard working with the Lewis group, and she figured out a way to print. It wasn't actually a liquid crystal polymer. It was a clay composite that had cellulose fibers in it. And when you put the material down, the fibers would align with the extrusion direction, like parallel to when you put the toothpaste out, right? And I tried to make a picture of that here. I think that's her picture. And then when that material was, cross-linked and solidified, they would put it in water and it would swell, but it swelled less in the direction where the fibers were. That kind of prevented swelling. And so something that was printed flat would fold up into a flower shape. Very impressive. Okay, so we can do the same thing with liquid crystal elastomers. We can 3D print. When I say we, I mean Taylor Ware, Dick Brower, and Tim White, and Jennifer Lewis, also the same group at Harvard. They did that. So here's, for instance, a 3-dimensional object that can transform into another 3-dimensional object. Okay, so this method is like I print something in 2 dimensions, and then when I stimulate it, somehow it becomes 3-dimensional. Here we can make one 3-dimensional shape that goes to another 3-dimensional shape, and it actually can like undergo a popping transition. Or did you ever have one of those little toys? It looks like a cup, and you push it down in the middle. You put it on the table, you push it down in the middle, and after like 15 seconds it pops. These things pop, but they might pop in response to a change of temperature or shining light on them. This particular experiment was changing temperature. So this one says room temperature RT, and this one says 200 C. It's gone from something that looks a little bit like a sombrero cut off at the top to something that looks like just a cone cut off at the top. So these are different ways of preparing the sample. And just to give you another example of how things change with light, this is work by Natalie Katsonis at the University of Twente. And this material is one that's doped with this azo dye and will change shape when you shine light on it. Okay, and what's really interesting is the chemists have worked very hard to make different varieties of the azo dye where the transition from trans to cis and cis to trans can be slow or fast. Trans to cis is driven by light. If you just wait for a while, it will eventually go back to trans, which is the lower energy state. Or you can actually make it move faster by shining a different wavelength of light on it. And there are even some materials that after you transform them, if you don't shine the other wavelength of light on it, it will never go back. It will sit in the metastable state for a really long time. So that's a chemical engineering problem. How do we make azo dyes that will let us switch things fast when we want them to switch fast, switch slow when we want them to switch slow? It's now a design parameter for making these materials. So, okay, so what's my challenge? I'm the computational theorist. I have 2 goals. Number one, I want to be able to simulate the process by which, if I know the shape of the material, I know the pneumatic director, and I know what is the mechanism of stimulus, to predict the motion. That's the first thing. The second thing is, if I know the shape I want to get, in principle, I should be able to design a pneumatic director field that will give rise to a shape transformation that I would like to achieve, for instance, because I want to make a robot or something that's going to like reach out and pick a strawberry, whatever thing. I haven't achieved that yet, but it's a goal. So one really important thing, I really don't like to show equations to people in the afternoon because I know it's hard. So I'm just going to kind of wave my hands a little bit and tell you about what the math is. And then you can forget about it, okay? So the first thing is, this is a Hamiltonian. What does a Hamiltonian have? A potential energy and a kinetic energy. Okay, the easy one is the kinetic energy. I'm going to describe my elastic solid by a mesh of points connected by lines defining tetrahedral volume elements. It's a divide and conquer mechanism. I'm just going to describe my continuum solid as a set of tetrahedra. Okay, that's the first thing. So that's a mesh for the material, and I'm using a finite element method approach, okay, which means I need to know an energy. So the first thing to do, let's get the kinetic energy out of the way because that's really easy. Let me imagine as an approximation that all the mass is in the mesh points, in the nodes. Okay, so imagine I had a big block of cheese, since I'm fixated on cheese today. Big block of cheese, and I want to or maybe tofu. Tofu is good. It's kind of stretchy. It's stretchier than cheese. And I want to describe how it goes wiggle, wiggle, wiggle on the plate. Jello is also pretty wiggly. Okay, so if I just put, maybe it's a tetrahedron of Jello, a giant tetrahedron of Jello. Imagine I put one node at each corner, and I said I'm going to put all the mass of this Jello, 1/4 in each of the nodes, and then ask what is its moment of inertia. And it would not be anywhere close to the real moment of inertia of the real block of Jello, right? Because the real block of Jello has mass distributed throughout its volume. And if I put all the mass in the corners, the moment of inertia would be way too high for rotation around any axis. Okay, but what if I take my block of Jello and I bake many tiny little tetrahedra inside? And I say, well, each tetrahedron has a certain amount of mass, you know, the density times the volume, and I'll just put 1/4 of it in each node. Each node belongs to many tetrahedra, so it'll get a little bit of mass from each tetrahedron it belongs to. And then I ask, what's the moment of inertia, right? It means I've just taken locally all the mass and put it into little bits. Then the moment of inertia will only be slightly changed. Okay, so what I'm going to do is imagine I have my object, it's got many tiny tetrahedra making it up. I put the mass in each one, so let P be the list of those little nodes, and the mass of the node times the velocity squared with a factor of half. That's the kinetic energy. Everybody in this room is a physicist, or many of us, so we all know kinetic energy. The rest is all potential energy. So what do we have? Okay, we have strain. Epsilon ij is a measure of strain. So the material has some reference state, a relaxed state where there's no strain energy. Like you're all very calm now. Are you in a relaxed state? I hope I haven't put you to sleep. Okay, and then you can imagine taking that little bit of material and you can stretch it, you can shear it, you can do all kinds of things to deform it. And then it has a strain, but the strain is measured by a relationship between its current state and its reference state, and that's represented by a strain tensor, okay? And then it has some matrix of elastic constants like the yield modulus, the Young's modulus, I don't know, different ways you can describe elasticity. It might also involve the Poisson ratio. Okay, and then each element also has a volume. So we have a strain density that is essentially a quadratic function of the strain tensor, and that would be true to describe any piece of elastic. Now, as it happens, there are many, many potential energy functions for elastic. One of the names would be Mooney-Rivlin. Another one is Neo-Hookean. This one I think is called Saint Venant. I mean, there's just like different ones. I picked a simple one because it looked to me like Hooke's law, like 1/2 kx squared. Okay, instead of x, I have a strain. But it doesn't matter which one you use. I'm using one that was convenient to use. And then this term is the tricky one. It represents mathematically the coupling between mechanical strain and pneumatic order. And the key parameter here is something called the scalar order parameter. So if you threw pencils in a box and they're pointing at each way willy-nilly, they're disordered, right? And if you shake them a little bit and they're dense enough, they'll line up. The scalar order parameter measures the quality of how well they're aligned. So in a liquid crystal, when you heat it, this is a graph of the scalar order parameter as a function of temperature, and at the isotropic nematic transition, it drops to 0. That's a measure. So at lower temperatures, it's ordered, but it gets less and less ordered and then goes to 0. So in our material, we know as we heat it, the pneumatic order is changing. This term couples strain and pneumatic order such that when you heat it and the scalar order parameter drops, the material shrinks along the pneumatic director. And that happens because there's a coupling between the strain and the state of pneumatic order. But I will skip the mathematical details. I'm sorry, what? Yes. That's. I believe the pneumatic isotropic transition is normally first order. It's just a liquid crystal thing. So if this is the reference state of some element and this is the current state, I need to calculate the strain inside. What I'm doing is a linear interpolation of the displacement field. And so I'm assuming that the strain is constant inside each tetrahedral element. And so here's some simulations of just plain elastic stuff that isn't liquid crystalline. just a piece of elastic oscillating in space. So this is me learning to do mechanical engineering. Okay, so here, color is showing you strain energy density. Okay, so this material is just flexing back and forth. We call this dancing tofu. It's just showing you this is a very soft material. And so we're doing F equals ma dynamics for the nodes. So each node gets a contribution to its force from every element of which it's a member. And to calculate the forces, I need to know the positions in the reference state, the positions in the current state, okay, and I do an interpolation of the strain, and then we just apply the chain rule a few times to get the energy gradient, the derivative of the energy with respect to displacement of a node. This is an atypical approach to elastodynamics. Many engineers would do an approach where they have to actually diagonalize giant matrices to do a problem like this. What's special about this algorithm is, like molecular dynamics, interacting point masses in chemistry simulation, this one is local. Okay, and it's trivially parallelizable. So in molecular dynamics, you have a bunch of atoms and a pair potential, like, I don't know, the Leonard-Jones potential. Each particle calculates a pair interaction with every other neighbor in the immediate vicinity. Those forces add as vectors, and then we do integrate the equation of motion, F equals ma forward in time. Now all the forces have changed. We do the calculation again, wash, rinse, repeat, do it over and over and over, and you get a trajectory. We're doing exactly the same thing here. And because it's trivially parallelizable, we can do it in MPI, and we can do it in CUDA for the GPU. Are you guys familiar with using the NVIDIA graphics card as a virtual supercomputer? Except it's not really virtual, it really is a supercomputer. Integrating this code in CUDA gave us a speed up of a factor of almost 50. Okay, so it's really huge. So something that used to make us wait 2 days, we could do in an hour. So it's really golden. So we have a tool, fast 3D elastodynamics. Okay, so being a physicist, the first thing I wanted to do was if I don't add any dissipation terms, I should be able to demonstrate the sum of kinetic and potential energies conserved. And I looked at the user manual for common finite element tools that engineers use, like COMSOL and Abacus, and none of them said you could turn the dissipation off. Their codes would all crash. I can turn the dissipation entirely off, and so let's see what's going on here. So this particular code ran at 700 frames a second. That's fast enough for a video game, right? And so let's see. If we want it to actually relax to mechanical equilibrium, we have to add some kind of internal friction or dissipation, because real materials have. But if we turn it off, so what's going on here? So let's see. Blue is potential energy. Red is kinetic energy. And they're both oscillating up and down. This black line is not an axis. That's actually the sum of kinetic and potential energy. So it's extremely well conserved. So we can do physics with squishy elastic materials that have no dissipation. If we want dissipation, we can add it. But if we want to, we can turn it all the way off. So we can study whipping motions. This particular simulation was done with 50,000 nodes and 300,000 elements. We've improved our memory management in the GPU, and now we can do millions of nodes and elements. So and still do things fast. To give you an idea of what we've been doing lately, we use compute facilities at the Ohio Supercomputer Center. Here's one of their advertising images of their system. So they would have, let's see, 160 nodes that are equipped with an NVIDIA graphics card, and we use one at a time. We don't even have to use multiple nodes in the cluster. We can use one node that has 28 cores, and we can achieve about 1,000 type steps per minute with 1 million tetrahedral elements on one GPU-equipped node in the cluster. So that's about what we're up to. These pictures are just pictures of some finite element method meshes. So this one is what I would call a structured mesh. It's a cubic lattice where each cube has been sliced into tetrahedra. And you can see rows and columns, right? This is an unstructured mesh. Both are possible and are useful in different mechanical situations. Okay, so let's go back to the +1 defect. So this is a thin film of rubber that now has the liquid crystal feature. And so those lines represent the pneumatic director is pointed in a circle. And then when it heats up, it turns to a cone. But did you see in between, it has a little snap through instability? Okay, it's not infinitely thin. The simulation is done with a finite thickness. The thickness really matters. And so in between, let me run that one again. So as it starts to emerge, you can see it looks a little bit like a hat with the brim coming up, and then there's a snap through when the brim goes down. Eventually, okay, but there are many different types of topological defects possible. So here, for instance, is a -4 defect. So if I were tall enough to put my pen up here, I could actually rotate the pen in the minus theta direction 4 times going around that circle. Okay, different parts of this object have popped up and popped down. There's nothing to break symmetry between the top and the bottom, and so we get something kind of messy. Okay, and in fact, the experiment for that system was done by Tim White at the Air Force Lab, and he saw something kind of messy. We demonstrated that we could heat it from one side and then make it always pop in the same direction to break the up-down symmetry by creating a thermal gradient. And in that case, we get something that looks like, I don't know, I think I have something like this I used to serve deviled eggs. Or maybe it's like the thing you make orange juice with. Right? So then you break the symmetry and you can get always the same result every time and not something random. Okay, origami is a fun thing to do. Trying to get something that will fold is actually quite challenging. My grad student now, she's got her PhD, Vianney Jimenez Pinto. She's at Temple University now. She figured out a way to actually make a round folding box, which I found kind of cute. So they call this radimuthal. So one side has a radial +1 defect, the other one has an azimuthal +1 defect, and together it's called radimuthal. Not a very clever name, but anyway, it folds and you get these curved folded lines, which is pretty cool. I don't have an experiment to show you on that one though. Actually, there are some experiments that are done just with the disk, but not with the box. Okay, so here's the most fun experiment of all. So this experiment was done in Eindhoven by the group of Dick Brouwer. The chief experimenter was Helene Gelebart. So this is a thin liquid crystal polymer film, and there's 2 materials that are the same, just one's been mounted with a different side on top. And what I'm hoping you will see here is that light is shining from the left side, and they are wiggling. Did you see how the first one was wiggling? Let's look at it again. Okay, so in this one, as the light is shining, mechanical waves move from left to right. Okay, and then they switch the light to the other one, and mechanical waves move from right to left. And that's like really confusing. So let me tell you what the material is. Okay, so this is a blueprinted pneumatic polymer film. The director is planar on top. It means the liquid crystals lie parallel to the glass and parallel to the long axis of the film. On the bottom, homeotropic means oriented perpendicular, so the molecules are nose on to the glass. And in between, there's a gentle splay. And what's going on is they mounted, the first one had the planar side on top, and the second one had the homeotropic side on top. And this material is doped with this azo dye such that when any side is illuminated, the material will shrink along the axis of the pneumatic director. Okay. And then they saw this weird thing that when the planar side is on top, the waves move left to right, and when the planar side is on the bottom, the waves move right to left. And they wanted to know, could I use my simulation to try to understand why that happens? Because it seemed very curious. Okay, so we had to make a model about how light affects the material. What produces continuous photoactuated oscillation? And why does the direction of wave motion switch when you turn the sample over? That seems kind of counterintuitive. So we have clues. The clue, number 1, the oscillation only occurs if they have 2 different geometries. I mean, 2 different anchoring orientations on top and bottom. So if the splay geometry is there, they see oscillation, but if it's uniform planar or uniform homeotropic, no oscillation, number 1. Number 2, if you shine the light from the top, it doesn't oscillate. It just like changes shape and sticks. It only oscillates if you shine the light from the side. Okay, and the dynamics matter because the motion is not overdamped. The other thing they told me is that when you shine light, the material achieves its new state, its illuminated state, in about 1 second. And if you take light away, it relaxes in about 1 second. So that's the information we had. And here's the model that we built. We said, imagine if S is the scalar order parameter, the quality of pneumatic order in each little element, as soon as it's exposed to light, it starts to drop, and it takes 1 second to reach its minimum value. And if you put it in the shadow, it takes 1 second to go back to its original value. Okay, and so it has an upper limit and a lower limit, and it just transit between them. And then we had to do some ray tracing to figure out what part of the sample is in light and what part is in darkness at any given moment in shadow. So we have photo actuation and a thermal relaxation. So it's a super simple model, and yet it kind of works. Okay, so this simulation was done by Michael Varga, who's a grad student of mine. And so here's the material. It's, the ribbon is initially in a bow shape, so it's attached on the two sides. And then we shine light from the front here, and you can see mechanical waves are propagating along its length. So this one is for the case where the planar side is on top, and the mechanical waves are moving away from the light. So let's see. The top shrinks along the axis and expands weakly the other way, and the light exposed area curves downward. What's interesting about this one is you see how the wave never quite makes it all the way to the end. There's always one little bump there. The experiment actually looks like that. For reasons I can't quite explain, that's not what ended up in the paper. This is what ended up in the paper. So in this particular simulation, you know, the sample is a little thinner. Maybe the geometry isn't exactly the same. But here, the wave is actually disappearing on the end. It's not getting stuck. But in the experiment, it's a little bit stuck there. But in any case, when the light shines from the left, the wave propagates away from the light. This was a really simple simulation. We modeled 40 seconds of motion. It was less than 6,000 nodes, less than 20,000 volume elements. This code ran on 20 minutes. It wasn't requiring huge investment of computer time. And if we put the homeotropic side up, the waves move toward the light. So here I should mention color indicates the state of pneumatic order. So when the material's in the light, it's blue, and when it's in shadow, it's red. The blue one, when it's in light, that means it's disordered and shrunk, and the red part is relaxed and long. And so this explains why the waves move in the two opposite directions. And now that was kind of cute, but they did something even better. I should say Helene Gelebart did something even better. She took that material, and instead of clamping it onto the substrate, she attached it to a little thin, lightweight rectangular frame. And here light is shining from the left, and the material is crawling away from the light. So she's made a little teeny, I don't know, robot might be a kind of extreme word for what it is. It's not actually gonna like bring you your morning paper or anything, but it's entirely driven by light. There's no battery, there's no other source of energy. It moves in response to light. Okay, so, and then what happens if you flip it over? What do you think would happen? Oh, it's very light. I mean, I saw it in the lab. It looks like it's like the size of a piece of Scotch tape that's been cut in half in width. It's about that size. So they're, I don't know, 2 centimeters maybe? I have to look in the paper to get the exact detail. Not very. So let's see, here's the homeotropic one. And it's much slower, but it actually moves toward the light. So, I mean, it's like a dog playing the violin. It's not how well that it does it, but that it does it at all, right? But it's an interesting, it's light-driven mechanical motion. I have seen similar experiments performed by some other, Dick Valla's group at, Valla's group at the Air Force Lab. He has a material that responds to water vapor density, like humidity. And you can take a wet cotton ball and put it on the table, and the polymer will run away from it, right? So we have autonomous actuating polymers that locomote in response to gradients in the environment, which is just a curious thing that it could even exist. So I think this is kind of fun. Nobody's made a toy out of it yet, but I think it's not only a matter of time. Okay, so in case you really care about this and you want to read about it, I put a link to the paper. It was published in Nature in 2017. And in fact, if you want to look at any of my papers, I made a tiny.cc version that will take you to my homepage so you can find some of those references. Okay, more fun things. Remember how I said we can form materials between 2 pieces of patterned glass? One of my colleagues, oh yes? It's got traction. Those have traction, friction forces with the substrate. Okay, that's the one that's crawling. You mean the one that's attached? Okay, it's getting traction forces because it's clamped on two edges. So when it flexes, let's see, when you have a traction force, because there's no motion, it doesn't affect conservation of energy, but it does affect conservation of momentum. So for instance, if you take one of these light responsive materials, you can have a thin film mounted on the bottom with a uniform pneumatic director. This is an experiment by Tim White. And you shine the laser from this side, and it will bend down. And then the other side is in the light, so it'll bend up and it'll oscillate at hundreds of hertz. Okay, so momentum's not conserved. Why is it not conserved? Because there's a traction force that's holding it still. I mean, that's true for a diving board in general. It'll flop. It's because traction force. That kills conservation of linear momentum. Is that clear? Are you sure? Not 100% sure. Okay. The momentum is not coming from the light. I'm sorry, what? Okay, where could the momentum come from? It has to come from static friction with the floor. I mean, I walk across the floor.
But that doesn't violate the first level momentum conservation, does it?
When I ate lunch today, a very delicious lunch, and when I spend some of those calories to move, I can walk across the floor, and my linear momentum is changing. I'm exchanging equal and opposite force pairs with the Earth. And since, I mean, I'm a bit overweight right now, but nothing compared to the Earth. So it doesn't move much, and I move a lot. Okay, so anyway, this same class of materials, instead of taking them away from two pieces of glass, I can just take one piece of glass away. And then when it transforms, I have now a reformable surface. So imagine if you had a carpet and you could push a button and then like little ridges would appear in the carpet. It's kind of like that. It's a surface that can transform its shape, or little spikes would appear, or little dimples would appear. That might be helpful if you wanted to change the coefficient of static friction on your floor. Like, I don't know about you, but I don't like to slip when I walk on my floor. On the other hand, when I want to dance, I would like to have a smooth floor, right? Sometimes it helps to be able to slide a little bit. So one imagines some application in the world where we would like to have transformable surface properties of a surface, and we want to change the shape. So this work was done by Greta Babakanova, who is an experimental graduate student from Oleg Lervenchovich's group at Kent State. And she actually went to Eindhoven and learned from the Broer group how to prepare these materials. So what she did is she used patterned substrates. The substrates were patterned with the technique developed by another Kent State faculty member named Chi-Ho Wei, where he uses light to pattern the substrates, and we have arrays of topological defects. So she puts the same pattern on the top and bottom surfaces, puts the material inside, forms it, and then takes one piece of glass away. So here she has an array of defects, and when she has defects that are radial, I don't know if you guys can see, but at each one of these little defect points, the pneumatic director points out. That's radial. Okay, and in this one, they're azimuthal. They go around like a target, like a circle. Okay, and in one case, you get dimples, and in the other one, you get spikes. So she can program shape-transforming surfaces. Okay, so we wanted to figure out if we could understand how that happens. So here's a finite element model of the dimple case, and here's the experiment. Okay, this is just showing the shape of the top surface. So we can see how the dimples go. And we've actually also done some analytical calculations that indicate how the shape transformation should proceed as a function of temperature and the change of pneumatic order. So if you have plus one and minus one radial defects, you get indentations. I like to call them dimples. Okay, and then let's see, that's the comparison of the plus one and minus one. Let's try the azimuthal one. The azimuthal one gives you spikes. I guess that might be useful for something. What if you have another kind of thing? Not pure radial, not pure azimuthal, but something in between. Kind of interesting. You can get something that kind of goes continuously from spikes to dimples. And then we were able to do some analytical work to show how the deformation varies with that angle. Kind of interesting. I wanted to show you some. Another one, we can actually have a striped pattern. Here, the pneumatic director, we call it C-striped because this looks like the letter C right here. But what's happening is the pneumatic director, if it's horizontal, it just curves and curves and curves, just continuously rotates across the sample. And what's interesting about that is it makes an array of a parallel extended dislocation. So let's see, the C-stripe pattern is on one substrate, the other substrate has a uniform pneumatic director, and in between we get this array of parallel line defects that are in the middle of the sample that run along the film. And then when that material is heated, you get channels. Now, what could you do with a material where at one temperature it's flat and another temperature you have channels or ridges? Greta Babakanova has used that phenomenon, for instance, to capture colloid particles. Like you can capture them in the little channels and then you can release them by relaxing the channels. So shape transforming materials can be used to handle other entities that you might be moving around in your channel. So you can think about it as a microfluidics tool that could be engineered. I think I want to skip through some of those things about those structures. It turns out that there's some edge effects. If you have a sample which is not infinite in extent, the channels don't extend all the way to the edge. And so you might think, oh, I made a system and the edge doesn't quite work, I'll trim it off. But if you trim that off, the edge effect will happen on the new edge. So we have to figure out how we can get the channels to go all the way to the edge, or else just not use the edge parts. And we can also engineer systems to have, if we make a mismatch between the two sides, we can actually get like ridges and make them tilt over, so we can engineer all kinds of interesting shapes. But let's talk about some more interesting things. In the middle of your eye is something called an iris. Are you familiar with your iris? It's one of the most beautiful engineered light control devices ever made, and it happened just through evolution. And the iris has the ability to open and close in response to light. Okay? And another experimenter, Rudolf Zentel is the one I know. I guess the first author is Schulhaden, looked at the structure of the eye and was inspired to try to make an eye out of pneumatic elastomers, liquid crystal elastomers. So here he has a hollow disc, a disc with a hole in the middle. I guess I would call it an annulus. And the pneumatic director is parallel to the radial direction. And embedded in the pneumatic director is a little bit of wire. It's like a heating element, and it's curled up. Maybe it just wiggles back and forth along the radial direction. And when he heats it, he can make this hole open and close. So we decided we would model that too. And again, we can not make it even pure radial. We can do different angles. So here's one opening. And at a typical angle, you would get both a radius change and a rotation. But we actually found one particular combination of parameters where we could get a pure rotational actuation. So this would be a way we could rotate something. You can have an actuator that actually rotates without changing the shape of the annulus too much. So it's just, again, a fancy actuator that can do different things. Here's an even more fun one. Imagine you had a pizza and you started to slice it, but you stopped the slice before you got all the way through the crust. This is an actuator that was developed by a scientist, I believe he's in Finland, and he designed it so that when you shine light on it, this object will open itself up. So it's another kind of iris. Instead of opening like a disc, it actually peels up, and when the light goes away, it goes back down. This is another kind of iris. You might use this, for instance, if you wanted to make something that would ventilate when it gets hot. You could have holes that open and close with temperature. And okay, I think it might be kind of fragile. These slices are likely to tear, so I'm not sure how practical it is, but it's an idea. You can have materials that transform in response to light or in response to heat for different types of structures. You can see it from the side here. Kind of cool. And I know we're running short of time, so I just wanted to show you a couple of other fun things my group is working on. Our finite element model can also be used to model colloids. So we can have small squishy objects. This particular simulation is in 2 dimensions. As you can see, these objects are being squished, kind of like in the Count of Monte Cristo, right? You squish something. And the color here indicates strain energy, and you can see that as they come closer and closer together, they form faceted interfaces, and then they have these cool transitions in their structure. So it turns out that the community of physicists and chemists who study colloids and their colloidal glasses and their response to strain typically model these things as hard objects with Hertzian contacts. And that's great for many systems, but if they're highly constrained and you get that faceted behavior, that's a really inadequate model. Finite element has been considered too slow for that kind of thing, so we're trying to develop tools that would enable modeling this kind of thing in 3D. And we're trying to make tools that can be used by members of the community. But there's no reason they have to be round, so just for fun, we did triangles. Right, so you can see we could do squishy triangles, we can do colloids of any shape. Anybody here interested in active matter? We're also doing simulations of self-propelled polymers to understand dynamics of crawling bacteria. In this particular simulation, you can see that when they're very, very flexible, they look differently than when they're a little bit stiff. So there's so much work going on in active matter right now. At the last March meeting, I think there were at least 8 or 12 sessions devoted to active matter. It's an extremely busy field at the moment. And let's see, I can show you some more active matter. Maybe I'll show you. We can also put active matter on curved surfaces. So this is active matter on hills and valleys. So we can understand how topological defects driven by curvature arise in active pneumatics. And I think I will skip the next few things and just show you who my collaborators are. So I mentioned this is the team at the Technical University Eindhoven, and Helene Gelebart and Dick Brouwer. My husband, Jonathan Selinger, is an analytical theorist who's participated in many of these projects. Manuel Valera is a faculty member at Slippery Rock who's been doing some of those colloid simulations. These are my graduate students. Actually, all of these. This one is graduated. This one is graduated. This one is in process. These two started a company and are busy making gazillion bucks in artificial intelligence, which is also a cool thing to do. So I think what I'll do is I'll put up a conclusion slide, and I'll be happy to answer any questions you might have. Thank you very much for your attention. Mm-hmm.
On the slide with the hills and valleys,
Mm-hmm.
you can create the entire material as hills and valleys, but can you select like one location for a valley, and then can you tune that across the material?
We have not done, but I don't see why not. Why would you like to do that?
I was just curious.
Well, in this particular case, the shape is fixed, and we are not having it respond to the material crawl over it. However, I'm also interested, the way cells locomote on a substrate is really affected by the mechanical properties of the substrate, as well as how sticky it is, but if it's compliant. And we're familiar with that. If we walk on sand, it feels different on our feet than we walk on concrete or carpet. So I'm actually interested in using the finite element mesh to give myself an elastic substrate and then put objects crawling on it and see what happens. Maybe not those kinds of polymers, maybe a more 3D image of a cell that's moving in some more realistic way. Yes?
How is the splay geometry made?
Okay, here's how it works. We can, when I say we, I should say the experimenters, have different surface treatments which promote liquid crystal alignment in different geometries on the substrate. So when the substrate is rubbed, okay, then the liquid crystal wants to lie parallel. And there are some other ways to do it, but that's one way. For the homeotropic anchoring, that's done with a self-assembled monolayer. So you put a chemical entity on the surface that has surface tension such that this is the lowest energy configuration. So that's called homeotropic anchoring. And because anchoring plays such an important role in display engineering, it's a well-developed set of tools. And so what's interesting is that when Tim White wants to pattern a substrate with those targets or whatever thing he did a pixel by pixel model. So he put some material on the substrate which can be aligned with polarized light. Then he shines a thin beam of polarized light and does 1 pixel and 1 pixel and 1 pixel and 1 pixel back and forth across the sample one line at a time. The method that my colleague at Kent State, Chi-Ho Wei, developed uses plasmonic metamasks. So again, there's some material that's sensitive to the polarization of light. He's made a mask with these tiny little slits in it, and he shines light through it, and poof, the whole system is anchored in a pattern. what's fun for me, for instance, another set of work I've done that I didn't include in this particular talk, we can take a pattern that has a bunch of +1, -1 defects on it, just like is used in some of these experiments. And then, did you ever play the game of Twister? How does Twister work? You've got like a red circle here and a red circle there, and you have to like touch both of them. Okay, so we can have topological defects in the liquid crystal, those pneumatic defects that are called disclinations, and they'll have one foot on one defect and another foot on the other, or an end on the other defect. And so you get like McDonald's golden arches of defects connected by disclination lines. And they undergo transitions with electric fields. They can be used to make all kinds of interesting liquid crystal display innovations. You guys know e-paper, right? You can get a Kindle, and you only need electricity to write the pattern. You don't need electricity to hold the pattern. There's some thought about making liquid crystal displays that have defect structures that can be metastable, so you can hold images in liquid crystals. So there's lots of reasons to try to engineer liquid crystal defect geometries. They're also just kind of cool. Yes?
So you mentioned that your code is easily parallelized?
Yes.
Because it's all local. Now, when you show the crawling material, now if you're modeling the light transport, then
Yes.
the solution is not local.
Right, so what we did is at each time step, we have a configuration of the mesh. Then we calculate the rays of light coming in. We figure out what part of the material is illuminated and what part is in shadow. So that has to be done separately from the dynamics.
Okay, but do you assume that the material is thin, optically thin?
That's a really good question. We assumed that the light only penetrated like the top 10% of the sample. So the back is not getting much. The reality is much more complicated because the distance that the light transits through probably depends on the orientation of the liquid crystal, but we made like the simplest model we could. Okay, so we just assumed it only affects the top 10% more or less of the film that it strikes. There's another issue, which is that we have interactions with the substrate. Okay, so we have to decorate the surface of the sample with like those nodes on the surface have to have an interaction with the floor. And so then it's like molecular dynamics. You have to find your neighbors, and we just used a short-range repulsive potential for that. Same for colliding colloids. So you have two squishy objects which have a mesh. When they come close together, you have to find your neighbors and repel. Otherwise, they'll ghost right through each other. I have a great cartoon of Casper the Friendly Ghost trying to catch a baseball, and he misses, and it like passes through his body and lands on the floor behind him. It's like, yeah, that happens in our simulation if we don't, because things will just ghost right through unless we introduce surface interactions. So yeah, it's like mechanical engineering was a steep learning curve for me. But here's the thing, my mechanical engineering approach is not standard. My finite element algorithm is not how mechanical engineers do this. And in fact, I went to talk to the experts in this field when I was developing this model, and they said, it will never work. It's not how it's done. And I said, but look, it conserves energy. It conserves linear momentum. It conserves angular momentum. And they said, maybe it works. I don't know. Anyway, I've been using it for about 10 years now, and it's serving me well. It is possible to make it a better model. We have a linear interpolation of the strain inside each element, which means it's a very low order finite element representation. We could use a more advanced version, but this one's getting me a long way.
I have a question. This active matter that you said.
Mm-hmm.
So how does curvature changes the topological defect?
Okay, so first of all, we know from studies of just the simple model, like the XY model, that you have an attraction of +1 defects to regions of high Gaussian curvature, an attraction of -1 defects to regions of negative Gaussian curvature. Okay, these are pneumatic though, so they should have topological defects of only +1/2 and -1/2, but the same effect should arise. In this particular case, I mean, I can show you that video again. This is unpublished work. Michael Varga went to visit Luca Giomi and did these simulations, but we haven't finished them. Okay, so what's going on here? Imagine you had a pet snake named Sally, and you take your pet snake for a walk, and you say, hey, Sally, let's go over the hill. And Sally says, oh, please don't take me to the top of the hill. It bends my back so much, right? They just avoid the top of the hill and the bottom of the valley because the potential energy is higher, right? So you tend to get hollow, tend to get hollow spots.
Because they are steep, they avoid it.
They have a bending energy. They have a bending energy. The other issue is, yeah, you can really see it there. This system is not dense enough to be necessarily truly pneumatic. I think we have to study this system at a higher density to get a better picture of what's really going on. You can see this simulation. This is actually one that I did. It's on a completely flat space, and it's like, it's confluent. Like, there's hardly any open area. There are still giant density fluctuations, as you would expect in an active pneumatic. We've also been modeling the experiments of Zvonimir Dojic, the ones with the microtubules. I'm sorry I didn't put the video in this PowerPoint. But in that case, the microtubules are driven by kinesin motors that attach to two tubules and drive them in shear. And so yeah, we're still pursuing the work in active matter. It's a challenging field, but we're still working on it. Again, Varga went to work for my other student's company, so he's not making much progress on his dissertation right now. That probably happens more in California than in Ohio. But yeah, I'm delighted that their company is making big bucks. I tell them the same as I tell all my other students. When you're rich, can I come swim in your swimming pool? And I hope they'll donate to support the graduate students coming up behind them. Yes?
Regarding this material that does this wave under the light, is there sort of a finite lifetime to that, or can you shine this on it for years? This goes on?
No one has tried it for years. I know they've done it, I would guess probably for hours. One issue though is that it does heat up because it's a very intense UV light, and the polymer might over time, the cross-link density might change. So I don't know how long they've run it, but I've seen it in the lab. I mean, I went to visit. I've seen it run in the lab for a while.
But there is a certain restructuring going on.
I would guess also it's a question of how hot it gets. But that's a materials question, and I use the pristine mathematical equations that don't include the fact that the material degrades with time. But yeah, I can check with the experimenters. Even if you put it in the drawer, like 5 weeks later, it might not work. It might not just be exposure, it might just be age, because the material changes with time. I had this experience, I have a couple of sons, and my older brother has also a boy who is a few years older, so of course they wanted to do hand-me-down clothes. And so as their child outgrew clothes, they put them in storage. And the storage was a shed in the backyard, and they live near Dallas where it's super hot in the summer. And then they were so proud to give me these big bags of clothes, and I would take out a pair of shorts and say, oh, these are so cute, how big are they? And I'd pull them apart, and when I let go, they wouldn't go back. Why is that? Cross-link density changes at temperature. The elastic was completely destroyed by exposure to heat. They all went in the rag bag. They couldn't be worn by children anymore. So yeah, polymers have finite lifetime.
Does this thing scale down to the microscopic? What degree? I mean, everything, most of what you showed us were macroscopic.
All my simulations have been at the continuum level. However, there are some. Oh.
Has anybody actually been able to do this with micron-sized polymers?
I wouldn't doubt that it would work, but to be practical, the big challenge is the other way. Can you make something big enough to pick a strawberry?
It all depends on what you want to do.
Okay, there was just a really nice article. I'm trying to think. It was yeah. There's an NSF competition right now. The full proposals were due like 2 Fridays ago, maybe 1 Friday ago, 2 Fridays ago, that was for soft robots. And so I'm collaborating with a team at Rice, and they are making small robots that can crawl around, but not just driven by light. They're driven by electrical current that creates heat that causes contraction, and it can walk. So my job is to model the device. Okay, so here's the hard part. Literally, the hard part. I've been modeling soft materials. They're going to build a robot. It's going to have crispy, rigid pieces. How do you model a soft thing attached to a hard thing? If I tried to mesh the hard thing and put in the mechanical properties for the hard thing, I'd need a tiny, tiny time step to model mechanical waves propagating across that thing, and I'd never be able to do anything. So what I said I would do in the proposal, I haven't done it yet, is I'm going to treat the hard objects as fully rigid and model their deformation using quaternions. So their center of mass can move and they can reorient, but they won't squish at all. Everything around them can squish, So it's an elastic body coupled to a hard body. So it's just, again, it's a applied math challenge. Okay, so you have the soft object that's meshed. The hard object also has to be meshed for heat transfer, but for deformation, it's just going to be a rigid object that can rotate and translate. It can rotate around any axis, and it can translate in any direction. So that's a challenge for the next graduate student to help me code. But that's not really a deep progress in physics. That's just, from my point of view, an applied math challenge. But see, we're physicists. We fear not. We can build it. And we'll build it, and it will run fast on the GPU, and we can outrun all the mechanical engineers. That's my plan. But I mean, you could do this with COMSOL. You can make a rigid object and a soft object and attach them together, and COMSOL already knows how to do it. It's just new for me. But are you concerned about finite size effects? You think when it's really small, it won't work?
No, I was just thinking it'd be neat to do.
You're thinking what?
It would be neat to do.
What could you use it for? That's the key issue.
Something you can inject in somebody and develop emotion.
I just saw a story this week in Chemical Engineering News. Little helical shapes, little corkscrew shapes with a magnetic moment in fluid. You can make them rotate by applying an external magnetic field, which they said was as weak as the magnetic field from a fridge magnet. And it makes them spin. And when they spin, they locomote. Okay, so you've got, they swim kind of like the way spirochetes swim. Those are the class of objects that include the beryllia that causes Lyme disease. And they spin around. And actually, I've been wanting to model beryllia. And I have a pre-proposal pending on that too, because we can make dynamics of actuating bodies. Why not model the actuation of a nanobot? In this case, it's actually a single-celled organism. And it's an unusual creature because instead of having flagella in the water, you know when it's cold, you put your arms inside your sweater? Its flagella are inside the envelope of its outside membrane. And so when the flagella move, the whole object corkscrews, and it swims by drilling through. So beryllia can swim in highly viscoelastic fluid. Is that something you'd like for your nanobot? Well, if I can model the beryllia, maybe I can design a liquid crystal elastomer that will do the same kind of motion. But first I need computational fluid dynamics, which is a tool I don't have, but I found a colleague who does, and we're hoping to work together. And we also found a biologist that can measure the forces and torques in the actual swimming little creature, and hopefully we'll be able to build a physical model. And you want to make a fake one? I mean, they already have a rigid one. It doesn't swim at all. You just spin it with a magnet and it drills. So you may not need, okay, the difference is beryllia is not spun by an external force. It swims itself this way and it drills through the fluid. It's astonishing. Such a thing exists in nature. I'd also like to model how fish swim and how rays swim, so rays with their propagating waves. So I really need computational fluid dynamics. That's the next challenge for me also.
Let's thank Robin.
Thank you.